Okay, let's try this. I turned my Bluetooth microphone off. Is this better? Okay. So sorry about that. Thanks again, Mike. You can take it from here.
No problem, Carl. Thanks. Thanks for the chance again. So this is week 3. These are the topics we'll cover today, and it'll be different than it was certainly from the first one, and even different from the second one. So the overall flow will be, I'm going to go through a bunch of PowerPoint slides that I pre-prepared. All of the models that I will discuss are available for you to then use on your own should you desire. And this will make sure, last time I think we did a much better job of getting information out there, and this time perhaps at the end we can do a little bit, but we'll get even more information this way. And then at the end, if you guys can feed back to Carl what we could do in the future that would be better, that would be great. Okay. We're going to add a transmission line, and then I'm going to show you what it looks like. And then I'm going to charge you with a question and a challenge. And then we're going to cover insulated wire and its impact on antenna response and how to implement it. And then we're going to generalize our dipole model, which was already made into variables. We're going to make that so that it's more general and it includes the antenna length as a direct variable. And then we'll use that model to learn a lot about dipoles that at least I did not know when I started out. And also to show the power of using the variable format. And then we'll take that building block, that dipole model, and we'll build a simple 2-element beam. And then we'll optimize it until we find a pretty good beam with an SWR that is essentially a match for 50 ohm coax, which I did not know was possible, given all the Yagis that are out there that need matching sections. So, and last, we'll take the dipole that we've been working with in a horizontal and inverted V and upverted V, and we'll turn it into a vertical dipole with 4 elevated radials to introduce the vertical format. Okay, these are the file names which I put up at the Google Drive. You guys can all access them. So let's add a transmission line. So let's start with the NEC card. So this is the NEC card format, TL format. Transmission line, the wire number, the segment number that you start from. So it's just like the network card. You have to set up a wire to start the transmission line. And then you have to give it a target wire or port, they call it, wire number and segment number. You give it an impedance, which for coax is 50 ohms. You give it a length. You give it an admittance, which is 1 over the impedance. Then you give it a length, and you give a real admittance part for port 1, and then the imaginary part for port 1, and then admittance for port 2, and admittance for the imaginary admittance for port 2. So you have 2 ports, 1 line, 1 transmission line, and the 2 ports are basically 2 wires or wire segments that you have to span. Okay, so how that looks in the model is, this is our same model we used last time. It's just a dipole with these variables defined, which does not include the length of the antenna, but it does produce a dipole of various configurations. So now the transmission line is down here. So we start the transmission line from wire 5, which is just a fake wire that's been put in place simply to start the transmission line. And we end up at the center of the dipole where the feed point is. Okay, the impedance is 50 ohms. The length is 5 meters. Then I give the first admittance for port 1, 0 and 0. And then the admittance for port 2, the real part, 0.008, and we'll talk more about how I arrived at that later. And then the imaginary part is 0. So we start here, we end the transmission line here. It's 5 meters long, it's 50 ohms, and it has a mysterious admittance, which is ostensibly 1 over the resistance, which should be a pretty big resistance. Okay, and we also have the EX on the actual transmission line, okay, which is this wire. So that's where port 1 of the transmission line is. Okay, so we built a little antenna here, a dipole, and we've added the infrastructure of a transmission line card. To make the transmission line work, we need to put the transmitter on the wire that begins the transmission line and feeds the antenna. Okay, so if I uncomment this TL and uncomment this and comment out this EX on the antenna itself, I end up with something that looks like a transmission line. Now I put wire 5 down near the ground, so it would actually look like a transmission line, but you don't have to do that. You can put it anywhere as long as it's distinct from the feed point connection. So that's how it looks in 4NEC2. It's a nice visual. You can see the transmission line is present, assuming you give it a wired, location that makes sense. Okay, so now this is the implemented transmission line into the model. It's you can see that the EX is actually on wire 5.1, which is the beginning port. And so let's go to some results. So I ran the model without a transmission line, and then with that admittance that I already showed you, I ran it with a transmission line. And you can see that a transmission line that's lossy, which all of you already know, causes and I played around with the admittance until I got nearly a 0 SWR. But if you've ever raised your antenna and then tested it halfway up with a short coax and then hooked up to 70 feet of RG8X, you've seen this kind of effect, perhaps not this profound. But the coax, once you hook it up, will broadband the apparent response of the antenna and lower the SWR. Okay, now that's typically how a transmission line works, and now you know how to put one into place in your own model. And the consequences of a transmission line are, on the left, we have the antenna producing 6.83 dB. That's the no transmission line case where the transmitter is hooked directly to the antenna. And then when I have a lossy transmission line, I lose a bunch of gain, 4.75 to 6.83, so 2.25 dB. And that's also normal for an actual transmission line. It's, it robs power from the far field. Okay, now I have a puzzle for you guys. So there's a lot of people out there who know a lot more about electronics than I do, and electricity and electrical engineering. So when I came up with this transmission line, I knew, and I apologize for my voice, I knew that a transmission line lowers the SWR and it broadbands the response. And so I searched around until I came up with an admittance that maximized that effect. And however, to me, it's a nonsensical admittance, because if I inverse this, it's a huge resistance. So I am puzzled about this actual value, and the way I came with this value was trial and error until I got this value. Now, if I put in 1 ohm, which is 1 mho, which is much less resistance than the value that I put in to come up with an admittance of 0.008. And remember, admittance is 1 over the resistance. And in this case, if I'm 50 ohms, I don't have to worry about the imaginary part. So if I just put in 1 ohm and I rerun the model, I end up with minus 12.1 dB gain, which is basically the antenna has been completely extinguished from emitting anything, and the SWR is 50. So I wanted to introduce the transmission line, and you can make it work as it should, but assignment for the class, why does 0.008, which is ostensibly 1 over the resistance of the transmission line, and 0.008, I can't remember what that is, but that's like how many ohms? One moment. All right, 1 over X. So that's 125 ohms, and that gives a perfectly reasonable response for the transmission line. But then if I put 1 ohm in, which should have less effect, I get this weird effect. So either there's something wrong in NEC, or I don't understand something, or there's something wrong in the model, but there's nothing wrong in the model. I know it. So if somebody in the class wants to take a closer look at the transmission line, by the way, this next week I might, so I also have access to EasyNet because it's free now. And I can go into EasyNet and implement a transmission line as well and see if it gives the same result. I just haven't had time to do that yet.
What
But one of
happened?
you guys might actually know that A, this is an okay result, and you might even know why. If you do, please let the whole group know through the reflector.
Have you tried 0.02 as admittance? Because that would be 1 over 50 ohms.
No, I have not, but at the end of this class, if we have time, we can try it. Or you can try it because you have access to all the models.
Hi.
But I mean, I've tried a lot of stuff and I have yet to understand the transmission line. So I can make it work though.
Okay, I think
Yes.
the issue is not the transmission line. The issue is that you put a 125 ohm resistance in shunt across your feed there at the end of the transmission line where you're feeding it.
Okay.
So 125 ohm is going to give you a little bit of loss. It'll help even out the standing wave ratio. It's not as drastic as what Comet and one of the other manufacturers does to make a wideband vertical that covers all bands with a SWR of 1.5 or less, which is to make a very lossy matching network. But the reason why you're seeing a SWR of 50 across the entire band when you put a 1 ohm resistor across your excitation segment is that the SWR of a 1 ohm load is 50. So what you're seeing is just it's just seeing primarily the load with some parasitic thing, which is a antenna with a transmission line on it that's just contributing a little bit of noise to the situation. So a 1 ohm shunt across your feed is going to give you a 50 to 1 SWR. So no surprise here.
Okay. Well, thank you very much, John. That's a fantastic explanation. I partially understand it. And the question then becomes to implement properly a transmission line where you want to have a way to simulate the resistance of the transmission line. Where do you put this admittance? You put it on the port 2, which is the antenna itself, or you put it on port 1, because that's the only two places you can put it.
If you could back up to the format for the TL card, please.
You bet.
Okay, there we go. So, so this does assume that you have a lossless transmission line, because you can only put in your characteristic impedance in ohms. The way that you would, the simplest way to simulate a lossy transmission line would be to have a complex characteristic impedance. That's the characteristic of a lossy transmission line, is that it has not just a real component to its characteristic impedance, but it also has a reactive component. What you might have to do is at one end or the other put in the equivalent parallel resistance.
Oh, okay. Well, that's a different load card.
I think you could put it in this card here, but it would be frequency dependent. So I think, yeah, it would be frequency dependent. So yeah.
Okay. Well, thank you very much for explaining.
Well, thank you.
this. Well, so what I did was I faked out this transmission line until I found what a real transmission line does. However, the way I did it doesn't really make sense, and I guess there's definitely a better way. You can use a load card that has a parallel resistance. There is a load card for that, and I might do that for next time. At any rate, this is implementing the transmission line in obviously a kind of an unusual way, but it ends up giving a transmission line result that's consistent with reality. All right. So there you have it. The ignorant guy teaching the class, but you get to learn what the actual card does. Thank you very much, John.
Mike, can I just ask another question about that chart? You got
Sure.
the one before that. You've got two lines on it. Did you do that manually, or does the software allow you to do that?
The software generates this for you, and we covered that once before, but I'll cover it again at the end here. I'll show you how to do all that stuff again.
Yeah, I know how to do it, but I didn't realize you could do two charts, get two lines on it, the lossy and...
Oh no, I did the two lines in Photoshop.
Ah, got it. Okay.
Sorry. No, you can't, it won't show you comparisons, no.
Right, okay.
Okay, puzzle challenge for the class. All right, insulated wire, here we go. So if you go down to Home Depot and you buy wire, you can buy it not insulated or you can buy it insulated. It's usually actually cheaper to buy the THHN stuff. Since I've used that extensively, I have implemented it into all my models. So I've put it in here because it's kind of interesting to know what insulated versus not insulated wire does. THHN is very common. A lot of people have built their antennas from this, field day, whatever. And it does impact, how the antenna behaves, and particularly its length at minimum SWR. And here's all the different THHN wire specifications in terms of its diameters, what you need, and all of that stuff. I separately had to look up the dielectric constant for nylon or PVC, which is all out there. But how do we implement a insulated model? We use version 7 of the load card, which is only implemented in 4NEC2 as far as I know, because NEC2 does not have insulated wire. Now it might be that EasyNEC has done the same thing that 4NEC2 has done, but the load card 7 you have to know the dielectric constant of the insulation and the radius. And then you just build it like you would any other card. So on the left, I have a bare wire antenna. And on the right, I have an insulated antenna, which is the same antenna, but the wire is insulated. And you can see I have 3 load cards for the 3. You apply it to each of the wires and you give it a dielectric constant and a radius, etc. Now, interestingly, you can actually specify pound 14 THHN. And, oh no, that's the comment, my bad. So this is the load card and with all of the appropriate information. And when you implement the load 7 on each wire, each segment, or if you implement partially the insulated wire, it actually shows a visual of the fact that it's insulated. On the left is the uninsulated model view, and on the right is the insulated model view. Okay, so if you run these 2 models having optimized the bare wire for 14.35 and then simply put insulation on that wire, and you then run and find out the minimum SWR, it's 13.9 megahertz. So insulated wire actually significantly can lengthen the electrical length of the antenna and change its characteristics substantially. And you can even see this when you're building antennas with bare wire versus insulated wire, because the bare wire is always shorter. Okay. Now, that's the end of the load cards and the various different ways to add all kinds of stuff to your antenna system that's not the antenna model itself. Okay. So now we're going to take our dipole model, which we built last time in variables, but those variables did not include the length of the antenna. And so we could not directly optimize the length of the antenna for anything. So this time we're going to develop a model that has the antenna length directly in the model, so we can optimize on the antenna length and optimize on the angle, which is a much more direct way of dealing with the model. And it's also how we actually deal with the actual antenna. Okay, so this is the old model we had and the variables that we used. And in that model, we used X distance, which did give us a dipole model. It did give us 3-dimensional coordinates, but it nowhere gave us the length of the antenna. So it's a little bit, when you're optimizing, it's a little bit of effort to extract out the length of the antenna after you're done. So let's fix that. So we're just going to use some very simple trigonometry, and we're going to rebuild the same exact antenna with angles and the length of the antenna. So we just write down 2 simple trigonometric identities. Sine theta, well, here's theta 1 and theta 2. So sine theta 1 is equal to x1 over leg 1. So x1 is equal to leg 1 sine theta. And let's see, cosine theta is equal to z1, this length here, over leg 1. All right, so z1 is leg 1 cosine theta. And same exact thing over here. So just some high school stuff here. And then we have to come up with the coordinates of the left side, these coordinates, all 3 of them, and we have to come up with the coordinates here. So we have this distance, this total height, h, we know that. We need these coordinates here, and these coordinates are h minus z1, that location right there. Okay, that's the height of the end of the antenna. If it's down or up or flat, regardless. Okay, so now if I write down these three coordinates in this coordinate system, which is not numerical, I have x1, this distance, is leg 1 sine theta, y is still 0, and z leg 1, this location right here, is h minus leg 1 times cosine theta, theta 1. And the same exact thing down here, except for, oops, I made a mistake. That should be theta 2 there. I'll change it. That's what I get for cut and paste. Okay, so this is our little model for an inverted V. And now let's code it into the actual neck or neck 2 format. Okay, so we have the ability to define all of these variables first. So the angle is going to be 90 to start. We're going to get leg 1 to be 5.0729, which is what we were using before. X leg 1, as we previously noted, is equal to leg 1 sine angle leg 1. And then the Z leg, that it's a little bit obtuse in terms of my change of, so Z leg 1 right there. So Z leg 1 is equal to center height minus H, which is leg 1 cosine angle 1. Okay. Same thing for the other side. So this is the left half of the antenna. This is the right half of the antenna. In terms of its coordinate definitions in symbol format, now we build the wires. So just like before, we do minus X leg 1, and now I did put minus center offset in here because that looks like our previous model. That's actually not completely correct, but hang on. It's not completely correct because our previous model doesn't have center offset. Okay, so we have 0, Z leg 1, that's X, Y, Z. And then we have a center offset, which we carry over from the previous model. That's the center little piece of wire, 0, and center height. And then we have that little piece of wire in the center again. And then we have the right side, which is X leg 2 plus center offset, etc. Okay. So we have this model looks almost identical to the way it looked before, except now Z leg 1 and Z leg 2 are the length of the antenna, the main length of the antenna. So we can optimize it directly. Now, if we want to adhere specifically to the model, this is the antenna model. So instead of trying to follow along with what we did before. So we have angle is 90, leg 1 is the same length, 5.0729, etc. 2 legs, left leg definition, symbol definitions, right leg symbol definitions. Now we only have 3 wires. Before we had 4 wires because we had this little bitty centerpiece for the transmitter to make it dead center of the antenna. Now, if we think a little bit, we can get dead center with the transmitter with 2 wires by just mildly thinking just a teeny bit. And then this will be exactly the model. So minus X leg 1, 0, Z leg 1. That's just X leg 1 and Z leg 1 shown in that picture. And then the center height, H. I should have actually put it as H. And then we have the second wire. We no longer have that little piece in the middle. We just have 0, 0, X, X, Y, Z. Whoops, what happened? X, Y, Z, that's the height. And now X, Y, and Z, which is the leg, okay? All right. So we have all this stuff here. and it's all coded into trigonometry in the definitions. So the actual antenna wires look very simple. And there's only 2 of them. And I put the EX on the first wire at the very end, which when you jam the wires together, ends up being right in the middle. And if you look up at the Google Drive site that I gave you guys a link for, you'll find these 2 models up there, and you can play with them. And they're one is without the offset, one is with the offset. The without the offset, they're both almost give exactly the same result, but without the offset is the one that is exactly the match for the model. Okay, so now let's look at this model and compare it to the results we had from our other model. Now, in this case, I'll be using the model that has the offset built in. So if we keep everything the same and we put all these new little definitions in, we should get exactly the same result. And we do. We get 6.72 dBi at the same exact max angle. Okay. So we were successful in making a new model of an old model and getting the same result. Exactly the same result for the frequency sweep because we had optimized it to be at 14 megahertz, the minimum SWR. Okay. So let me stop and say, when you build your model in the symbol format and you're thinking about the XYZ coordinates, there's a lot of ways of doing it where you can encode the links that are relevant to you and the angles that are relevant to you outside of just doing straight XYZ transition to variables like we did the first time for the first model. We just took XYZ and we transferred it over to symbols because that was the simplest start. But when you get ready to build a model and you're going to especially like build let's say you build a 3-element beam. You can start by building one of these little bitty models and then put them all together, which we'll do today for a 2-element beam. Okay, that's it. Now, we did all this work to explore a dipole, but can we learn anything about a dipole we didn't already know? Well, for sure, that was possible for me. So I'm going to walk you through all the ways that you can take this simple model and learn something new using the tools that are 4NEC2. Like what antenna configuration offers the maximum gain? Because whenever I work with people at my field day, they're working hard to try to get it to be a flat top because they say that's the maximum gain. If we drop it down in an inverted V, we'll lose gain. Okay. Is that really true? And what antenna configuration offers the min SWR? We know that's an inverted V, but what kind of inverted V? And where's the maximum gain when it's a minimum SWR? So there's a bunch of questions we can ask just about a dipole. Even though, at least when I got started, I thought I knew the answer. Okay, so let's find the configuration with the maximum gain using the tools that 4NEC2 gives to us, okay? And the direct approach is to use 4NEC2 optimization. We can select the angles as variables, and we can select gain as the constraint. So I've gone through this with you guys before. I go into and I calculate and I start the optimizer after I've already run the program once, so it has a base. And then I select the angle, the 2 angles, which is 90 degrees. I say, oh, I want a maximum gain. Then I run it. It runs and it comes up with a maximum gain of 6.8, which is almost exactly the same as where we started. Slightly different angles, right? 98.8, 97.9. Okay. And it's bowed upwards. So that's odd. So let's keep going. Let's look at the phase and the magnitude of the currents. Why would would an optimizer return an upward bow for the max gain, even though it's hardly any different in the gain? So this is the current and phase for the flat top. All of these guys are parallel to each other. They do not interact at all, the magnitude and the phase. But when I bow it up slightly, the magnitude and the phase of each leg begin to interact by adding. So now I can get a higher gain by bowing this thing upward, and the optimizer bowed it up a little bit and then stopped. So the optimizer for 4NEC2 is like the vast majority of optimizers, and that is it does a local search around the starting point. Now you can get some optimization packages with MATLAB where you can make a wider search range, but the wider you search, the longer it takes, and also the less stable the outcome is. So Ari Voers, when he coded this up, he makes the steps around your optimization not too wide. So if you want to explore the antenna across a wider gain, a way to do that is to explore near areas in SWR, which is a smaller range number. So let's optimize this antenna for the lowest SWR. And let's see what happens, because SWR is a smaller number, and chopping up that number in a small area is a larger gain distance. Oh, I ran it. So now I ran the optimizer for the angles with SWR as 100%, and I get a cool SWR, 1.2788 down here in the lower left, which is way below 1.56 for the flat top. I have angle outcomes at 116.72 and 116.85. So I take these angles and I put them back into the model, since they're optimized now, and I explore the model. So now I have this model that's something you could string between two trees and let it hang down with the feed line. And you can see that the phase and the magnitude of the currents are overlapping. And in this region, they're adding, okay? And that gives you 6.86 dB compared to 6.72 dB, but the SWR is now 1.2788. So assuming that you're feeding this thing with a feed line, you have done two things to enhance the capability of the antenna. One, you reduce the SWR, so you have less loss. Number two, you've increased the gain. And you have done that by bowing this thing up, which is sort of how you would do it if you just strung it between two trees and let it hang down. In fact, sometimes that's all you can do. And that happens to be the best configuration for a dipole. So I found this interesting because I always thought that a flat top was the max gain. But the flat top is actually the maximum SWR. And it's the max gain as long as you don't look at this configuration. So because the inverted V that points down at the ground is lower gain because the legs are closer to the ground and ground losses take up some of that gain. Okay, so here's our new antenna, and it looks like we changed its resonance point from 14.15. I mean, from 14.0 to 14.15 with that angle change. So it hardly mattered in terms of its SWR bandwidth and its resonant point. Okay, but let's look at that. Did I call that right? It's 14.05, I'm sorry. So let's look at that. So it's 1.24, which is almost the same, and the gain is 6.88. So at resonance or slightly near resonance, it has the same result. Okay? And this is just a kind of a gratuitous 3D view to put a plug for the 3D graphics that that Ari Voor's built into this tool. It's just nothing like it. It looks good, and it actually gives you a whole bunch of information visually, because on the left, the colors are coded. So you can see the huge nulls on the right, the gains going forward and back, etc. Any questions? So how many of you have already knew that an upverted dipole is the best configuration? I'm curious. So when we did this, so I do field day with the RDXA, and we do an 80-meter dipole. And I worked with the guys to get it all up there, and our 80-meter dipole was hanging down like this. And it really bothered one guy, because he's a nice guy, don't get me wrong, but he was so convinced that we should try to work harder to get it to be a flat top. And no, I haven't sent this to him, but definitely stringing the endpoints and letting it hang down quite a bit, that's a good thing to do.
Mike?
Yes.
I've got a quick question. That's about K2OID. The actual dipoles aren't in a V shape. They're actually in a catenary. And if the actual geometry of the emitting elements are important, what does a catenary do to change the shape, to change the gain? It must do something. So
the catenary means what to you?
Catenary is what a chain. If you hang a chain between 2 points, the geometry of the chain it defines is called a catenary.
Oh, okay.
It's not going to be straight. It's going to be an ellipse, almost part of an ellipse. And in this case, those aren't going to be straight. They're going to be steeper at the ends and more horizontal as you get towards the middle.
You mean in a real wire situation that can bend?
Real wire situation. You know, when I hang antennas and I'm up in a tree, back when I used to do this, and looking at it, it's not straight at all. It's very curved all the way down. It's just a great big curve.
Well, I'll tell you what, we can so that's a good question, and you can answer it. So what you can do, or anyone in this class can do, and it's simple, it wouldn't take very long. You don't have to make a continuous curve to get a good approximation. You can break this up into 5 sections, and then at each section, you can make a wire, and then the next section is a little steeper, and the next section is a little steeper yet, until you get to the length that you want on the 5th section, which will be the most steep, and then run it and compare with this model. So I assign you guys to do that, although I'll do it just to see what happens. But next time, who asked the question again?
I did, Bob, K2OID.
Okay, Bob. Next time you get to present this result.
I'm not sure I'm up for running the model yet. I haven't watched the other two sessions on tape, and they're very interesting, but I got to dig into it a little. If I have time, I will.
Well, the existing model's there, so you can take that existing model. Actually, it's not hard, Bob. If you want to work together to do it sometime, just give me a call or shoot me an email. And at any rate, you after this class, up to this point right now, you are capable of answering that question for yourself.
Yeah.
But it's a very interesting question, because I didn't think of it. Because when I saw ours, the 80-meter one, it's got such a long length, and the feed line was so heavy that it looked more like this to me.
Okay. It's interesting. Just finishing up. It's interesting because you've got to generally have a balun up at the feed point. I support the balun, and what I have is 2 catenaries, and it would be interesting to see what my antenna is really doing.
Well, you can.
Okay, thank you.
You can definitely simulate as many
too.
little segments as you want.
Yeah, I'll take a look at it.
It will be interesting. Actually, I'm sure what's going to happen is if this area is flatter down here and goes out further and then this area curves up, the interaction, which is where the extra gain is coming from, will be less. But you can prove that.
Okay.
Because the reason that this gain is going up is because,
The distance. Yeah.
yeah, the phases are overlapping and adding. So if it's flatter down there, that'll happen less. Okay, so the optimizer searches for a local minimum and a local maximum. All you guys who have used MATLAB's tools know that. And if you want to look in a different location, you got to start it at a different spot. Okay, so that's optimization to find the maximum gain by actually searching on the maximum SWR or on the minimum SWR, which turns out to give the maximum gain as well.
Mike,
Yes.
this is Jack, W2STM.
Hi, Jack.
Hi. Oh geez. The difference in gain, your optimization, you're dealing with decimal point gain differences, right? 6 point.
Correct.
It's really small things, which would be very difficult to see in practice. So I'm not totally buying into that. It's better to bow the antenna the way you have upward, just because you can get 0.12 dB or whatever it was additional gain. So that's one comment. The other comment, and I wonder what you think about it, is I wonder whether I've played with using 75 ohm coax for feeding antennas. 75 ohm coax is cheap, readily available and cheap. You have to be careful whether you get it with sufficient braid coverage. But anyways, dipole is basically a 72, 75 ohm antenna. So the SWR reference to 75 ohms would be very low, and you could see that on 4NEC2. And then if it's perfect, you connect it to a 50 ohm transmitter, the worst, your SWR is 1.5, which is, ain't so bad, certainly acceptable. Any comments?
So everything, first of all, everything that you said is insightful and correct. And so definitely in terms of implementing an antenna that is a dipole, that's a flat top. I have a friend, you may know him, Dean Faklis. He only uses the 75 ohm cheap stuff because the losses are so much less than 50 ohm. But in this case, what I'm trying to do is show you guys how to use this model with the tool in a simple way so that you don't get scared off in the first session. And using a little dipole where I have made a little model so you can see how to use the symbol format and then optimize it is just an educational tool. And the fact that it kind of reveals some interesting things because yes, it's 6.8 dB compared to 6.72, which in all reality is identical, but you've also lowered the SWR from 1.56 to 1.24. So if for some reason you can't do anything but this configuration, like in our case at field day, then there's no reason to get excited about it not being a flat top because it's actually better. And that was really my main point.
Yeah, I agree.
And so, a lot of like when we're at field day, we get these, we string it up between these big trees and it hangs down. And for whatever reason, there's a guy that's just freaking out that it's not a flat top because that's the maximum gain, but that's not the maximum gain. So, or the minimum SWR. So I was just showing this. It's not like you will design it this way, But if it ends up being this way because you're working at field day and you can't make it any other way, feel happy. So that's really the main message. And, you know, you have what I think is a good little model to work from that you can then turn into, as I'll show you, you can turn it into a beam, which then offers even more cool stuff you can do. All right, so where were we? Jack, did that answer your question or address your question?
It sure does.
But yeah, what you say is true. So, and then Y optimization, we already covered that. Okay, so I just wanted to show another way to use the model now that we've encoded the lengths. And again, there's nothing that you guys don't already know, except that if you go in and you change the angles, you can see a lot of different types of dipoles and how they behave. And here's just one of them. And the reason I chose this one is specifically because we have eliminated a null. So we've decreased the gain quite a bit from what is it, 6.72 down to 5.21, which you might see in the real world, but you still got a fair bit of gain coming off the end here. But let's say you're at field day and you wanted to build a way to get the East Coast and still have a dipole. So you could have some gain off of this side by just sloping this guy a little bit. And you can see I don't actually have the number for the gain over there, but you can read it. It is 4, let's see, 0. So it's like 1 dB. It's not that great, but it's better than this huge null. So just a thought and another way to play around with the model. And a cool view of the graphics again. And to make this happen, once you do it, so to make this happen, if you code your model all up in numbers, will take a while and it'll be mistake prone. But if you've done it with the variables, it takes 2 seconds to make this antenna. And that's the power of the variables. And the last slide on this is, up to this point, the mast that we have been using to hold this thing up, the metal mast, because it's mostly been orthogonal up here or not interactive, now the mast plays a role. You can see that we're inducing electricity on the mast, and the mast is acting like a reflector, which helped eliminate that null. So you can, when you go into Fornec 2 and you're analyzing, you can see where the currents are being induced, which really helps sometimes to learn stuff. Okay, now let's see. We built this single element dipole in a very flexible way. So let's make another common antenna, which is a beam. And then let's see if we can make it work better than the dipole with all of the tools we have. Okay, so the concept is going to be, we're going to start with our one dipole, and then we're going to take a clone of that one dipole, and we're going to put it together so that we have two dipoles along the y-axis, exactly along the y-axis, spaced out by a distance d. So the distance between these two, I will call d. So here's the whole model, which you guys can have, already have. And you can see the only difference from the previous model, all this is exactly the same. I just cut and paste this, and then I come back and I say 3, 3, 4, 4, 4. Everywhere that I saw 2, I put a 4. Now I have two dipoles that are exactly the same with different variables, and I'm going to space them out with d equals 4 meters. And then I build the wires. So here are the variable assignments for the two antennas. And here are the wire coordinates for the two antennas, which is just, again, cut and paste, but change from 1 to 3. change from 2 to 4. And assuming that I pick a D that makes some sense, boom, I have a beam, a 2-element beam antenna. Right now, I don't know how effective it will be because all I did was clone, and I've spaced it out by a distance D that I can adjust. Okay, so once I built this, D was unknown, so I played around a little bit for this class until I came up with roughly 4 meters as the max gain. And I did that manually because the optimizer searches in a small region, and I can search wherever I want by just typing in a number. So we're going to start in this class with 4 as the distance here, and each element is 5 meters. So it's about, the distance is about half of the antenna length, a little bit less. Okay, so let's look at this. I have no idea what kind of antenna this is. All it is a clone of 2 dipoles, and then I messed around with the distance. Okay, so let's run the far field pattern. Now, the first thing I want to take a look at on the right. So you can see now that the current on the antenna with the little circle here, that's the antenna that is being driven. That's what they call this the driven element. And you can see a nice big arc here. But on this element back here, you can see that the current magnitude is not quite as big, but it's still pretty big. So we're getting some reflective inducement effect, which you can see here. Now, I apologize if I rotate. So this looks like the antenna is actually pointing in the different direction than it is over here. But that's an artifact of the angle that I'm actually viewing this at. And I could have easily changed it so this was pointing in the same direction as this. But I already built the slide and I decided this is actually how it defaults to look. So at any rate, now we're getting 10.82 dBi compared to 6.72 dBi. Now that is enough gain to be noticed. And all we did was put 2 dipoles together and then move them 4 meters apart. We haven't done anything else yet, and we made ourselves a beam. Now, we're not 100% sure we can use it because we don't know what the SWR is. And this is the 3D view, just a gratuitous, nice, beautiful 3D view. But you can see we now have a big null down here in the middle. And all of that former gain is going out here. And it's 10.8 dB, not bad. Okay, so let's look at the frequency to sweep. Well, goodness, we do have a nice low SWR. It just happens to be out of band. So, and we've hardly done anything except put 2 dipoles together. So let's fix that. So I ran the optimizer on SWR response, and I took the results, I put them back into the model, and it was like 5.0 meters exactly for each one of them. And now we're back at 14 megahertz with a very low SWR, still 1.24. Is that right? Well, it's hard to say. I think it's right around 1.25 or something. So very low. Okay. Now, if I actually change, so I optimized it and I made the minimum SWR at 14 megahertz. Now I went back and looked and see if that impacted the far field gain, which previously looked like this. So you can see we had 10.82 and we have a kind of a smallish backward radiation, smallish. Now, let's see, frequency sweep, yep. Now, when I moved the frequency to 14.0 megahertz after it's optimized, you can see this rearward projection. It's pretty big. So we lost front back ratio and we also lost forward gain. Now it's 10.07 dB, but we are at the minimum SWR. So can we fix this? So we can clearly see it now. Here's where this 3D view is really useful. You can see that we have a beam, but we're not, I mean, we're putting out 10 dB, but we're also putting out a lot in the opposite direction. Now, that might be okay to go from 10.9 dB to 10.1 dB and be able to pick up, let's say you're pointing southwest, pick up Maine during field day. But let's go ahead and let's optimize on SWR with the leg lengths and see what happens, because we haven't done that. So we end up with leg 1 being 4.938 and leg 4 being 5.1085, which you can see down here. But the most fantastic thing is we're using 1.0, we end up with an SWR of 1.04, which I would not have thought was possible. But when you have two different elements, it is. You can basically use them to come up with a very small SWR. Now let's see what happens. Let's see if the gain is gone. No. We have a 2-element beam with a native SWR of 1.04 with 10.86 dB, and off the back, 1 dB at the most. So what we've done is we've made a little 2-element beam that costs nothing except to hang find two trees that are roughly 4 meters apart, and then put them both up there and run your field day like this with pointing southwest, and you really wouldn't do so bad. So now what we did is show, what I'm trying to show here is, this is a very compact little model, and it gives us a nice little 2-element beam. And we ended up with a 2-element beam that has a perfect match for 50 ohm coax, 10.8 dB forward gain, and a pretty good rearward gain, but you could probably still get Maine in your logbook during field day. So it's not too bad, not too bad at all. And it's also, oh, and here's the actual frequency sweep after all of that work. At 14 megahertz, we're at 1.0, basically SWR. We have a reasonable bandwidth, but because we've optimized for gain, we've optimized a few things, we no longer are as broadbanded as we previously were. Okay. So, questions about that? That's basically doing some cool little building block to make a 2-element beam, and then using 4-neck tools to find a kind of a cool configuration that's actually useful as a beam. And no Yagi, nothing, just 2 pieces of wire. Questions? Okay. Now, previously, we did not use a flat top with the maximum gain. We did optimize our little dipole, so at some weird angles. So I put those weird angles in here, and I come up with a forward gain of 10.99 dB, which is higher than previous. What was it? Let me find it. 10.86. Now we're at 10.99. And I just hung it from the tree and let it dangle down. But if you look at the backside, we don't have as much rejection off the backside as we previously did. So can we fix that? Oh, and also 14.05, what is this? 14.15 is the new SWR minimum. That's pretty close to 1.0. But not as low as it previously was. Okay, so now if I change the model to 14.15 megahertz and redo this, the gain is 10.89, but I have great rejection off the backside, less than a dB. 10.9 dB going out the front, 0.9 dB off the back. That's great. That's a real beam. And all we did was string these guys up and let them hang 4 feet apart, and we cut them to those specific lengths. Okay. And by the way, all of this is just example after example of how easy it is to change these models when they're in symbolic format and to learn a lot quickly, because to do this with all numbers in the model will be impossible. So the 2-element beam summary: for a 2-element beam spacing of 4 meters, which is possible, we can improve gain by slightly more than 4 dB over a dipole with an excellent front-back ratio and an SWR of 1.1. And it's not impossible to build this, actually. Okay, so then the last model for today is a vertical dipole with 4 elevated radials. So this just introduces the concept. It's not a quarter wave. We'll cover something more complex in the next class. But this is a half-wave dipole, basically over 4 slightly elevated ground radials. And the model for that you guys have, it's in some, if you look at, oh, did I not include, I'm missing one slide that actually defines the variables. I'll put that back in. But you can see here is the model. Well, here are the model definitions, and I put them like this so I can show you guys that you don't have to have a symbol, then a definition followed by a symbol and a definition. You can string them all out. So here's 3 different variables as long as you put a comma between them, and then as the frequency. So I have, so I can tell you what high L is. HGHL is the top part of the antenna. Okay. I think, if I recall, HGHL, and HGHL is the bottom part of the antenna. And then there's a center offset. And there's a height above the ground, which is down here. If you look down here, the antenna is not touching the ground. There's a little green part down here at the bottom. Hopefully you can see that. So that is height above the ground, HGHL, the center plus HGHL. And basically you only have, you still have to have 3 coordinates, but you only have 3 points along this line. And that's this model. Center offset, all that same stuff. Okay, so let's see what this does compared to a flat dipole. So, which is kind of interesting. I've never actually thought about using a vertical dipole, but they have these infed half-wave dipoles. And so how do they perform? This I would think would be the best case, since there's no matching section, nothing. And what we have is an interesting pattern. It's uniform all the way around. It doesn't have any shape except a donut. And it has 0.14 dB gain, which is pretty small. Now, there is some pretty, well, which seems small to me. I'm not familiar with this antenna. This is my first experience to ever look at it. And it seems like using a vertical half wave would be your last resort, but this is how it looks to the model. And I don't know if you guys, anybody out there have ever used a vertical half wave? Okay. And there's the donut that it makes. And this is the SWR, 1.67. So unusual SWR. And that's it for the, oh, here, finally I have the, all right, so this is 1 meter above the ground and a much better way of seeing it. .1 meter above the ground. Oh, and then this is 1 meter above the ground. I forgot. So here it's 0.1 meters above ground. Here I moved it up just to see what the impact is, and the gain goes from 0.15 or 14 to 0.46. Still the same shape, still not a huge gain, same SWR. Well, 0.46 on everywhere. So this is how vertical looks uniformly. Okay, so that's all I have right now prepared for today, but I have some other things I want to show you. Are there any questions about this content that we just went through? No.
Yeah, I've got, anybody else here? I've got a quick question about back to the 2-element beam. The question is that most Yagis, and certainly the one I've got up on the roof, has got a gain, it's 3 elements, and it's got a gain of like 8 dB. I've never heard of this. Is that real life? I mean, are we missing something here? 10 dB out of a 2-element beam sounds like an awful lot. 10 or even 11 dB. 2 elements? Wow. Is that really possible?
Well, so what I'm going to tell you is this. I don't know if it's possible or not, but I do know this. I have a fairly, if you go to my QRZ page, you can see that I have a fairly simple / complicated antenna system implemented, and I have built that entire antenna system into Fornet 2, and all of the frequency sweeps that exist very closely match Fornet 2 if you take into account the RG8X that I'm using. And I have used, for my off-center fed dipole, I've used a tool that allows me to tell which directions I'm transmitting in by looking at the stations that are receiving me. And the patterns are very good. So at least in terms of matching reasonableness to my simple antenna system, it's possible. And in my opinion, having worked with Fornet 2 and knowing that universities use Fornet 2 in their departments of electrical engineering for antenna modeling, I think this is real. It's just that nobody ever bothered to play around. And so we could easily build these and test them and optimize them and learn from them. But yeah, I don't know about so the Yagis, I don't know if you have a shortened Yagi either. Like I have a shortened dual element and it's much less gain than this. This is a full element, right?
Yeah. I'm thinking of all Yagi, for example, the stepper Yagis don't have any traps in them. They're completely wire, it's just basically wire. Or it's a tape. It's a copper tape. But I don't think they're claiming that kind of gain either. I'm pretty sure. Could be wrong.
I have a comment on that, Mike. This is Jack W2STM. Bob, unless I'm incorrect, the ARRL has long required that gain values given for antennas be referenced to a dipole.
Oh, that's it.
So there's at least a 2.15 dB difference in gain between isotropic and well, a dipole has 2.15 dB of gain over isotropic to start with. Yeah. The other thing is compare the 2-element antenna that we just saw, the beam. Compare its gain, whatever it was, 10 something or other, with the gain of the pure dipole, which was 6 or whatever something or other. So its actual gain over the dipole was
6 dB.
4 dB or so.
Yeah, that's about right. Yeah, that was my original question. Was I must be leaving something out, and you're right. That's exactly it. It's first over a dipole versus over isotropic. So that answers the question.
By the way, I can set. So I chose. This is a choice. I can choose DBI or I can choose DBD. So if I had chosen DBD, these numbers would be lower.
Yeah, got it.
But I don't think there's any fundamental flaw in neck 2 or 4 neck 2. So I think you could build this, yes. And if it's a simple subtraction of DBD, I think it's 2.2 DBD difference. I think that, but I'm not sure.
Theoretically, 2.15 dB.
2.15, yes, that's correct. Okay.
Okay, good.
The other thing, as long as we're talking about gain, I might just throw out a comment that if you model one of the dipoles that we've been modeling over ground in free space, the maximum lobe, of course, will be at 0 degrees, and the gain value you'll see will be different.
Oh,
And,
yes.
you know,
It'll be
because
much less.
it's now a full hemisphere as opposed to a half hemisphere. So all of the stooch coming out of the antenna when you're over ground, ideal ground anyways, is now redirected upward to the upper hemisphere.
So that's the full explanation. I'm glad we have people here that can. So depending on how your manufacturer defines the gains, they could be in free space and in DBD, in which case the number that you would see would be drastically lower than this.
Yeah. The other, just a comment to that, is that the RaRa, it must have been at least 20 or 30 years ago, stopped the advertisers, stopped the manufacturers from advertising gain in QST, because apparently there are even some more tricks that they can play to boost up their figures, jack up their figures. I'm not quite sure what they are, but I do know that it appears that there are other ways of calculating gain that can be confusing. So looking at the model straight, I think, is the way to do it.
Well, I think if you choose, I choose DBI only because it defaults to that, and it was a good year before I knew I could change it. And by then I was used to DBI, and I always use overground because I just don't, I just don't know why you would build a bunch of simulations in free space, because you're never going to build an antenna that you're going to use in free space. So I've never done that, but the explanation that's been presented totally explains why, if your manufacturer is using DBD and they have simulated their stuff in free space and they're using those numbers will be fantastically lower than these. But the relevant thing is the 2-element beam compared to the dipole, which we're familiar with, is 4 dB improvement. Roughly 4 dB improvement, which is nothing to sneeze at. And you can get a reasonable rejection off the back end just by playing around. And we have a 1.04 SWR. And I do think all of that would be achievable if you decided to build it. Yes, I do.
Oh, that 4 dB would be very reasonable, because I just know without a model at all, if anybody who's got a Yagi and you listen to a station and rotate the Yagi, you can see that you've got 30 some odd dB off the side, and front to back is usually several dB as well. You can actually see it. You don't have to calculate anything. Just look at your S meter.
Right. Well, I mean, this thing that we just played around with here, just for the purposes of learning, is way less. If I threw 3 elements in here and I played around, maybe I'll do that for next time, but you guys can do it now. You can take a clone of one of those, cut and paste it, play around for about 7 minutes, and teach yourself what 3 elements would do. But it'll do pretty good. We got 4 dB with 2. We get at least, you can't get more than 4. Well, I don't know what would happen. I actually don't know what would happen. But maybe somebody in the class will do it and can present next time. Okay. So that's
One
it.
comment,
You bet.
one comment about free space versus overground. And it's really, at the HF frequencies, you're never going to be up in free space. Whereas with the higher bands, VHF, UHF, that kind of thing, then you may very well have your antenna elevated far enough up that is where you would be able to use free space as a realistic comparison.
That's a good point. That's like 10 gigahertz, for example. So, and 10 gigahertz, some of the guys in my club, they're in love with 10 gigahertz right now. I have never used it because it's pretty expensive to get it all put together. But yeah, these guys are going all over during these contests and using 10 gigahertz way up in the air, 30 feet, which the ground is pretty far away for a 10 gigahertz signal. You're right.
I think there's rules of thumb about how many wavelengths over the ground before you really can ignore ground effect.
I do not know what they are, but okay, so that's it. Now, what I'd like to do is use some of the rest of the time to show you some interesting, let me pick one of these. So I want to show you some aspects. Can you guys see this or clearly? Can you see the text and the stuff?
Yeah, I can see it.
Yeah.
Okay, so I want to show you some aspects of the interface if you want to use this and customize it. So what I'm going to do, I just picked a random model. I'm just going to calculate the far field pattern. Okay, so now this is what comes up as default. And if you, as I already illustrated, if you want to find the maximum gain at the maximum, you just press I, you move your cursor from the, you put your cursor on the guy on the left, this pattern on the left, and you press I, and it'll automatically find it, which is kind of a cool thing. And it'll also give you some limits, okay? And then you can come over here and you can click and you can see whatever gain that happens to be. So now, maybe you don't like these colors, okay? And you think magenta is hard to see on your computer. All right, so you can come over here to show and change colors. And the reason I'm showing this is because I have actually changed these colors because depending on what monitor and what resolution, different colors look better or worse. So if you come to the color properties, you can change the color properties of major grids, that's in the actual plot itself, away from black. You can change minor grid color. You can change the main trace color. And what is the main trace color? Well, let's see. I click main trace and I see that main trace is currently blue. So the main trace is this guy right here. So I can change the main trace to red, okay? Or I can change the main trace to green, etc. Now I happen to have gotten used to blue, so I'm going to put it back to blue. So, and then the indicator line is this guy right here, I think. Where is it? Well, now I can't get it to come. Ah, there we go. So let me go back. Oh, what happened? Show colors. All right, I'm not sure what happened there. So now I'm on this indicator line, and you can see that it is currently set to, it looks like, oh, I wonder which one. Well, let's see. That's odd. I don't know what happened to the indicator line now. Max gain line is no longer coming up, guys, so I'm not sure why. But, and then the structure, you can change the colors of the structure itself, which is over here on the right. Okay. And let's get out of this one and come over here to currents, current magnitude, and let's go to show. Now I can show near far field here as well. And now show change colors. So I can change all of these aspects here as well. The background, the axis, the wires of the antenna. Let's just click on those. So you can see that they're a dark color now, like dark purple or something. The excitation, you can change that color from red. The trace lines, you can change those colors. The open ends, you can change the color of the current from red to whatever you would like. Okay, so there's a lot of customization in terms of your visual, whatever. So let me change that back to red because I like it as red. Okay, so those are two things that you can do to customize if you're going to be using it a lot, or even if you're not, you can see different colors on different monitors much better. Okay, I just wanted to show that, and then I want to show calculate far field pattern. Now, if I come over here to 3D, I can see this nice little beam that we have here. Now I can go in here and I can select currents and I can see the currents. I can come in here and I can select the structure and I can see the structure without the currents. Segments, if you want to see all the different segments in the model. Let's see, wire, that's just the wires. And then that's all. You can hide the structure if you just want to see the pattern. So now if I hide the structure and come down here and say multicolor, I can see the pattern without the antenna, which sometimes is kind of nice. So you can customize the pattern. Let's go. Oh, that's pretty bad. I like multicolor much better. Okay, and let's put the structure back in so we can see the structure. And let's put the currents back in. And now you can see, you can rotate around and look at all kinds of stuff. And if you want to see the phase of the currents, you can. If you want to see both, you sort of can. I'm not sure about that. Sometimes depends on their amplitude, but here's the phase of the currents. So you can see that's kind of interesting. That's kind of interesting. And then let's see. So we got the magnitude already. There's the magnitude. I've never actually looked at the phase, but once for my dipole, it looked a bit different. So it's pretty interesting that it's pretty interesting that the mast does pick up some of the electrical, even though it's perfectly orthogonal. I guess I didn't know that. Okay, so that's actually, so customizing this interface, wanted to show you, hide the structure, that's it. So that's what I had for today. I don't really have anything else. I mean, we could take up some playing around if you want, but basically with the end of today, next time I'm going to, let me introduce next time. So next time we're going to build in simulation a model that we're then going to actually implement with an actual build and test it. It's something that I did during the pandemic when we were stuck at home. And the model is very interesting to put together and will give you a generalized vertical that you can then change going forward to any kind of vertical, quarter wave, half wave, whatever. But it's going to be a dual band 2 meter 440. It's actually sitting in my backyard right now. And it's what I use for all the local repeaters. And it works very well. It works actually better than the simulation. It works very well, and it was cheap to make. So many of you probably will have seen these before, but that's what's coming next time. And that's all I have for today, ladies and gentlemen, unless there's questions.
Yeah, I have a question. Well, actually, I have a group of questions. What I want to do, I've got 2 wire antennas in my yard, which I believe are far enough apart that they don't interact. I want to put another antenna in between them. So I'm planning on modeling all 3 in one model so that I can see how they would interact or not. 2 things that concern me. One is my ground is sloping. So one end of an antenna may be higher off the ground than the other end, but is actually lower in real height, if you see what I mean.
Sure.
And the other thing is there a way for me to model the roof of my house? Because that's a metal roof. So it's a big flat area, not a wire. And I'm wondering how that would affect things.
So I'm glad you asked that question. So the answer is yes, you can. Let me go here again. You can model your backyard antennas, and I'll show you something here. 1 second. Okay, unfortunately, all these are insulated, so let me get it. So here is my backyard. It's actually oriented in this way. So my backyard looks like this. If you can see, which is going to be difficult, I have an elevated vertical up about 30 feet, and it's then got about 24 feet after that. And that elevated vertical has some big, long 17-foot custom radials. And then attached to the mast or to the actual vertical radiator is a 20-meter dipole, a 40-meter dipole, and an OCF. So I can switch the EX to any of these antennas and see how they interact. And of course, they all interact like crazy, but sometimes that's actually interesting. So let's see what's actually. I'm afraid to look at what the model is because it won't be user friendly in any way. I just want to see where the EX is right now. Well, we can find that out even better, easier like this. So I'm going to calculate the far field pattern, but I have absolutely no idea which antenna is actually, so this is the OCF.
Right.
So here's the OCF, and let's do something interesting. I don't want the currents. Here we go, multicolor. So this is my OCF. As one of my friends told me, sure is a lot of this propagation pointing up. But this is my OCF, and actually, this is actually not the most recent version. So that's actually not, if you guys will just bear with me for 1 more minute. That was an old model. So here's my actual antenna system. So there's the 20-meter dipole, the 40-meter dipole, and the OCF, which has got my little homemade balun, and then this vertical, which works from 17 meters to 10 meters with the little custom, the radials are along these guy wires. So here's the SWR response of that OCF, which is fantastic in terms of band access. And here is the actual OCF for each of the bands. So let me see if I can blow this up so you guys can actually see it. So hopefully you can see this. So this is 10 meter OCF, 12 meter that looks pretty darn good, honestly. And then 15 meter, and all of these have very low SWR. And then what's this? 17 meter. These are all the high bands with the OCF. So, you know, if you have a vertical that covers 10 meters through 17 meters, and then you have an OCF that covers 10 meters through 17 meters, you can really, I mean, no, if you know the direction that these are in, the 6.7 dBi, then depending on the time of day, you can do really well. Like this afternoon, I don't remember when the 10 meter contest ends, but yesterday in the afternoon, I was doing really well off my OCF with these two lobes here. So at any rate, that's a long answer to, can you model your backyard? Absolutely, you can. And you'll learn a lot, and you'll be able to see. So it'll show you, like, let me see, you can see that here. So plus, plus, plus. So do you see these little currents here?
Oh, yeah.
So those are not being excited. Okay, that's interaction. My OCF is the one that's being transmitted. And all, well, not the OCF so much because I'm on 10 meters, but you can see that the 40 meter is getting some excitation, and that the 28.4 megahertz is getting some excitation. So you can see, you know, and you could turn this antenna off in a second just by commenting it out and seeing if some of this 6.7 dBi nice gain over here goes away. Because it might be that this is compressing this OCF downward, but I don't know.
Right.
So yes, you can, I'm telling you, I had so much fun simulating my stuff. I mean, that's how I actually, I was like you, I put all this stuff up in my backyard, and I had no idea how an OCF worked. I kind of knew how the vertical works, but even that is interesting. And once you put up all this stuff and you look at the vertical, it really changes the pattern dramatically. So what used to be an omnidirectional pattern is no longer.
Oh, right.
So,
Okay.
but yeah, if the only thing is when you get started, I want to give you some encouragement. When you first get started with Fortnite 2 and you start building the models and you start building the coordinates, I mean, you have to have a high, like, you have to have a high tolerance for frustration and mistakes, because in your early days, you're going to get confused about which coordinate you just mapped and this and that. At least I did. I'll give you my own personal, I'm like a regular guy that has to work for everything, right? Nothing ever came easy for me, and Fortnite 2 didn't either. And so when you get started, unless you're one of these rare guys that can do everything with ease, this is a little hard the first few days. But if you stick it out, just curse so that your wife can't hear you and get mad at you for getting, you know, for making noise, just keep at it and you'll get your full backyard antenna system built, and it'll be the coolest thing. And then after that, you might get interested in building something else for your backyard.
Right.
And by the way, we got a whole bunch of people here. Some of them are obviously extraordinarily knowledgeable. I'm not one of them. I just know how to make these little models. So if you get frustrated and you want help, ping somebody. I'd be happy to help you. Ping somebody, say, I'm frustrated, I can't figure this out. Email the model, I'll take a look. And there's probably a bunch of other guys that would be happy to do that too.
Okay. Yeah.
But yeah, if you, a little motivation and you'll have your whole backyard understood.
Thank you.
No
Just a
problem.
quick follow-up on Tim. He asked a question a little differently than I would. I've got an off-center, 80-meter off-center fed dipole also, and I live next to a stream, and there's basically half the antenna is a ground that is sloping down. Can you change, is there an option to change the geometry of the ground that your antenna is being built over to it having it slope at one point and being flat at another point, things like that?
The answer is there's no option to change the angle of the ground, but there's every option, let me show you, to change the angle of the antenna relative to the ground, which is really the important one. So just a sec. So here's my OCF, if I can find it. It's been years since I looked at this. Comment, OCF wire construction. Believe me, when you build these things, if they're going to be complicated with a whole bunch of stuff like this one, put in comments. So here's my OCF. And you're going to see that it's all done in variables, and it's done with directly programming. I don't have the angles. So the way you would do that is you would take the model that we have built today, which is angle and length, and then you will change the length so it's 1/3, whatever the lengths are of your OCF, okay? And then is your OCF 200 ohm?
Yes, it's got a 4-to-1 bailing.
All right, so let me show you what you got to do. All right, so to properly get the SWR for an OCF, you have to come into settings and select char impedance and change it from 50 to 200. And then when you do frequency sweeps with the SWR, it will be proper 50 ohm representation, because putting this at 200 in the char impedance at 200 is the same thing as giving it a 4-to-1 transformer. Okay.
Yeah.
So that's the only trick that you need to know outside of just gutting through, changing that existing dipole to be an OCF.
Okay.
But yeah, you could, like I say, the models that I just put up there, you can start with any of those and change their lengths to be your OCF. And then if you want to tilt the whole thing, you just tilt it like the same way I did in the little exercise I showed you where the dipole was tilted. That's basically tilted relative to ground, and you saw the result. It makes a difference.
Yeah. In my case, I'd be tilting just the short leg of the OCF, because the other one's over, the long leg is over flat ground.
Well, I have a question for you. So you have an 80-meter OCF?
Yeah.
So
Designed by W2NED for me.
So I'll just cut and paste my OCF and email it to you. What's your email? Do you know my email?
Yeah, no, I don't.
Here, I'll give you my email. It's Mike, M-I-K-E, period, KM2B @gmail.com. So if you email me, I'll cut and paste from this giant model the subset that is the OCF and the other relevant stuff that you'll need, like the EX and all that stuff. I'll build you a little OCF model and I'll send it to you, since I already have one.
Okay, one of the things that I'm interested in doing is I looked at your website and saw the article on the OCF and looked at your SWR curves. And one of the things that's fascinating is we both have 80-meter OCFs, but mine works on different bands than yours does. Mine's got a null on 30 meters and nothing, and no null at all on 20 meters, and works on 17 and sort of works on 15. It's quite different than yours, and yet it's the same antenna, more or less.
Hang on.
It's not the same antenna, I know, feed points and all the rest of that, but.
No, tell me. So let me tell you what I did. So this response is different from your normal OCF, because when I built my OCF, I cut the wires 1/3 and 2/3, which I thought was what you were supposed to do. But I'm guessing, I'm betting you did not do that.
No.
Correct.
mine was mine was actually, I don't know if you know W2NED, Ned Asim, but
Yeah.
he designed it for me. And what he said was, what bands do you want? And I told him, I've got a Yagi, so I don't need 10, 15, and 20. I want all the other bands. And that's what he did. And that's what it does.
Oh, well, then he used simulation to give you the length that you wanted.
Yeah, he did. He did.
Okay, so
I
that's.
might add the simulations must be correct. One of the reasons I wanted to, when Carol told me about the course and missed the first 2 sessions, one of the reasons for wanting to come in was to take a look at that antenna, because I went from a backyard full of antennas to 2. All I've got is the Yagi and the off-center fed dipole. Gets me all the HF bands, even 6 meters.
Well, I mean, you got
And it
plenty to
works.
have fun with. Look what I got, a bunch of dipoles and a vertical. But you can have tons of fun with one antenna. But with
Oh, yeah.
respect to this response, so I made a mistake when I built it and hooked it up. And that was, which someone told me later on when I told them, I said, so I did mine 1/3, 2/3, and then I put the balun in between and I raised it up and I got this SWR. And it's been stable ever since I put it up. And, but most, I don't know of anybody else that has a 1/3, 2/3 OCF, because that was a mistake.
I can find out what this one is. Ned's got the design dimensions on it. I'll ask him.
Yeah, send all the dimensions, because you'll need to put it to change
Yeah, I
the
know I'll
program
need
that I send you. But I carefully measured everything and I put all those measurements into the model. And the model, the Fornet 2 model matches these minimums really well, except they're not as low. And the reason they're not as low, I can make them as low the reason they're not as low is because I'm feeding this with RG8X, about 70 feet of RG8X. So probably the SWR of the actual antenna is like 2.5 at 80 meters, but the RG8X makes it look fantastic. So this is actually measured SWR and it's not from the model.
Got it.
But the model has, with the same dimensions, the model has exactly the same minimums.
Oh, no, it's,
So at any rate, there's, I have at various points done stuff for other people or get enthusiastic about something. I'm currently not working on anything in the model except for this class. But at various points, people in my club will ask me to do something. Some guy asked me to build him a 2-meter. He wanted a 2-meter beam that did this and did that. And so I took a bunch of time and built one for him. But he bought one instead of building it. And then Dean Faklis used to ask me all the time questions about stuff he was doing. So I don't know if you guys know Dean, he moved to Florida. I can't believe it, but anyway, that's the course for today.
Can I answer Mike's question, Tim Barrett's question? This is
Sure.
Jack, W2STM. Tim, you can model the roof. You didn't,
yes.
You didn't cover that. By building a wire grid to simulate the solid metal. And I have an article by Seebeck, the late, right? And I don't know, I have it printed out. I don't know whether the link is still active or not, but I'll research that and put it up on the reflector or send it to you.
Thank you.
On the roof. And on your question about sloping ground, yeah, I don't think you can do sloping ground, as Mike said, but there is a function in NEC to allow stepped ground. Like if you had an antenna on top of a cliff and then going down to the sea, you'd want to be able to simulate that because you'd of course have a gangbuster signal. And there is a way to do it. I've never done it. And so I can't give you anything more than to say that I think something is possible, but probably really complicated.
All right. I'll look into that. Thanks, Jack. Thanks very much, Jack.
One more thing. I don't know if you guys are all ready to jump off, but so one more thing about the Fornet 2 install. So when you install Fornec 2, in the install directory, there's this directory called models. I don't know if you guys have gone to see it, but you should. So, and someone was asking me about loops, etc. There's loops in here. There's HF short, HF simple. There's all kinds of models in here that have all kinds of examples, from hundreds and hundreds of numbers defining everything to very complicated variable models. And some of them were done by Seebeck. You'll see his name as the author for some of these. So Ari Voers was working with Seebeck on some stuff. And even more amazing, if you buy the antenna modeling book, it comes with a CD. And every single model that they have in that book, plus a bunch more, comes on that CD. And this is all of them right here. So this is all of their models, okay? And guess what? I assume with the permission of the EasyNet guy, I forgot his name, Fornec 2, as I'm going to show you, Fornec 2, ARR, so you can see these are all done in EasyNet. Well, I went to the one directory where that's not true. So these are all .ez binary files. So the EasyNet format is binary. You cannot see the model. You don't have access to the .NET format of the NEC model because he put it into a binary format. But if I click this and click open, oh, don't tell me. Oh, wait. Yep. So Fornec 2 reads all of the .ez files that are out there, and there's a huge library if you spend the $20 to get the ARRL antenna book. It's well worth the $20. And then you have all of the ARRL models, and you have all of the models that ship with Fornec 2, which is hundreds of models. So if you get a question from someone like, oh, can I do a roof? There's actually a mesh somewhere in here that I've seen before that somebody put under a ground plane. So somebody wanted to see how a ground plane worked underneath basically a metal roof. And they put a mesh in there. I can't find it right now, but if you ask yourself a question, there's a really big chance between the antenna book CD and all of the models that come with Fornec 2 install that it's already there someplace, or something so close to it that you can use it and modify it. That's it.
I would have to look there.
Oh yeah, everybody should look in there because if everything's there. HF simple has got some dipoles. Sometimes they're numbers, sometimes they're in variable formats. There's just a huge library between. And once you open an EasyNet file from the ARRL antenna book, then you can save it off as NEC, and you can modify it to do anything you want after that.
And so thanks to Brian, who's just sent me a surface patch card to model the roof. So I'll take a look at that.
Very good.
Hey, Mike. I had a general question. Today you showed some of the 14 megahertz vertical and horizontal antennas. I'm wondering what everyone else is using on 14 megahertz. Should I make mine vertical or horizontal? I'm wondering about the polarization of the antenna and if it really matters.
So I'm gonna let you guys and I'm going to let somebody else answer real quick, if somebody wants to. So, okay, Yin, the high-level answer to your question is that in today's presentation, if you go to the link, I don't know if you're in groups.io, but if you go to the link that I put at the groups.io site, and you pull down the presentation and you go through it, then you can answer your own question, because in today's presentation, I cover the horizontal traits of a dipole and then the vertical trait of that same dipole. And I have all those models up there so you can even teach yourself what's in that PowerPoint slide. But at the high level, the answer is there's a profound difference between a horizontal dipole and a vertical dipole of exactly the same length. A profound, profound difference. And
So is
it's-
everyone else using horizontal then?
So there are both horizontal antennas that are being used and vertical end-fed half waves that are often used. Now, if so, and the reason somebody might use a vertical is because in general, not always, but in general, the vertical has a lower launch angle, although it has less gain. So you have to look at the gain profile of a horizontal. You can get, if you can get a dipole up high, that's your best bet. But you also lose, right? So it's really, so if you're using a vertical, you can transmit in all directions and receive in all directions, so that if somebody from Texas is calling you during the 10-meter contest, then you can get that guy. And if somebody from Europe calls you in the 10-meter contest, you don't have to miss it because your beam is pointed down at Texas. Or your dipole, the dipole has nulls off the edge in. So it really depends on what you want to do, whether you would use a vertical or whether you would use a horizontal. And also depends on your backyard.
Yeah, you were asking what other people do. I mean, I had a vertical when I lived on a small plot, and now I have horizontal wire antennas because I've got room for them. You also asked about polarization, and other people may be more expert than me, but my understanding is that once it's been reflected over the ionosphere, the polarization changes. So I don't think that's really a consideration. It is more if you're on 2 meters, but it's much less, I think, of an issue for a HF antenna.
So Yin, if you look at my screen again, you can see horizontal inverted V OCF, and you can see the vertical. So there's a vertical here and then an insulated OCF. I wish it wasn't insulated now because it would be easier to see the vertical, but these two, if you, I gave out my email. If you email me, I'll send you this model and I'll modify it before I send it. So it's a dipole horizontal, and I'll modify this so it's a vertical with the same frequency minimum. And then you can play around by switching the EX on each one of these, and you can see for yourself what the strengths and limitations of each are.
Cool, thank you.
So if you,
Let me add one more thing. I think Tim touched on something really important here. He used to use a vertical when he had a small lot, and now he's using a dipole. I think the important question is, what can you fit?
Yeah.
And then just use that. Any antenna that's in the air is better than an antenna that you're just thinking about, because you can actually use it. And once you gain some experience with just a piece of wire that you put up, then you can start thinking about how you can improve that within the geometry that you have to play with. So both antennas will work, and both antennas will get you on the air, and you will make contacts, but then eventually it comes down to, what's your big goal? What do you want to get out of it? And if it is DX, those rare DX petitions that pop up every now and then there's a pretty good chance that a vertical will get you there quicker than a dipole. Ideally, you put up a multi element beam so that you can swing that around and point it in the direction that you want to work at. And that will give you the biggest chance to make the contact. But in general, whatever you can put up will work for you and will allow you to make contacts.
That's exactly correct. Yeah, and my own constraints were backyard size and budget. And both my kids were in college when I started getting into, or getting close to college when I started. So I had like a total $3,000 budget, which rules out a Yagi because just one Yagi will cost $3,000. And so I just built a bunch of cheap wires from Home Depot and put them up, and I've had a ton of fun. I spent a little bit less than $3,000, including the radio and the coax and everything. And so my priority has been to have fun, play in the play in the little ARRL competitions they have, chat to some people on 80 and 40 once in a while, and basically just have fun for the least amount of money I could do. So it really, your constraints will be totally potentially different than mine.
And again, I'd like to add a little bit. I hadn't heard anybody mention anything about coils and traps to shorten antennas, but there are ways of making antennas shorter. They don't work quite as well, but they'll fit into even an apartment room, even an apartment building, that kind of thing. That's number one. And number two is we haven't talked about propagation conditions, but provocation, especially now with the sunspot cycles, are all important. And sometimes with even a crummy antenna and low power, if the band conditions are with you, you will work that station. And that's some of the most satisfying DX I've ever worked, was when I was running 5-10 watts and an antenna, and I just had propagation, and the other folks trying to work this guy were running kilowatts, but they were someplace else and couldn't do it. So don't put up the best antenna you can, but don't be discouraged. Radio is really magic. You can do a lot with a little.
Thanks, guys.
And if you need help, ask people. There's so many people in the community that will help you shoot wires into trees, pull the wires up, help run the coax. Don't hesitate to ask people for help. And next week we'll cover this shortened 2-element beam, because I forgot that I did it. And there's a cool way of, a shortened 2-element beam is not too exciting because you lose so much gain. But if you're stuck in a small backyard, then there's a way to shorten the beams. So we'll talk about this maybe next time as well. And I want to thank once again Carl for bringing us all together, sponsoring this kind of conversation. It's very good, Carl. Thank you.
You're very welcome. I'm learning a lot here, and I actually just sent an email to the Groups IO list with 2 screenshots that I made for my end-fed half wave. One on 80 meters, which looks pretty nice, and one on 10 meters, which looks very weird. The weirdness is explained by the geometry of my antenna, because I don't have 132 feet in a straight line. I go out and then take a sharp left turn for the remainder of the antenna, and that ends up with a very weird pattern. And I've experienced that when I'm on the radio, based on which stations I can actually work. And now I know why that is when I just look at the pattern. So what I learned here does actually does match my experience.
That's good.
So the pictures don't show up for you?
Yeah, they're not coming through.
Huh, that's weird.
It looks like something came through, but they're not showing as pictures.
Okay.
What format are they?
I would assume they're PNG. That's what I
You would think
usually.
that would, you would think
end
that
up-
would work.
Let me see. I'll take a look, and if I don't see them online, I'll just send it out again and make sure that they show up. Okay,
Sounds good. All right,
So-
thanks, everyone.
thank you, Mike, for doing this. As I
Yes.
said, I've learned a lot. I assume everybody else is in the same boat, and I'm looking forward to our fourth session next week, next month.
Take care, everyone.
Yes,
Take
thank
care.
Have a
Thanks,
So-
Mike.
great rest of the weekend. Bye.
Thank you very much, everybody.
Yeah,
Thanks,
thanks.
Mike.
It's great.
And everybody have a wonderful December solstice of their choosing.
Very good. Thank you. Well done.